Hello from beautiful Portland, Oregon. My name is Jake Karnes. I'm a managing consultant and penetration tester at NetSPI, and today we're going to be talking about CVE 2020-17049, the Kerberos Bronze Bit Attack. So this is a vulnerability that I discovered and reported to Microsoft back in 2020, and the patches and CVE for that were released by Microsoft in November and December of that year. Once the patches were out, I released the vulnerability details and an exploit for it. So we're going to be covering all of that today. I hope you enjoy. Let's dive in. All right, we've got the slides up and we're ready to go. So here's our plan for the day. To best understand the vulnerability, we'll start by learning about the Kerberos protocol itself. Now you might have heard about Kerberos before, but maybe you're a little unsure of the specifics, and this should be a great introduction and head start into understanding how it works. Then we'll be continuing into how Kerberos can be used to delegate authentication between different services within an environment. This is enabled by some extra extensions that Microsoft built on top of the Kerberos protocol, so we'll learn how those work. This first part is maybe a little dry getting into the cryptography and protocols, but I hope you hang in there with me because once we have that background knowledge out of the way, we'll dive into what the issue is and what security features it bypasses. With all the great knowledge and understanding in our heads at that point, we'll be primed for a demonstration of the exploit. We'll see how all these pieces come together, and we'll see how we can escalate our privileges and how we can start pivoting in the domain to further our attacks. So what is Kerberos? Well, it's an authentication protocol. This means it's used to prove who you are to other entities in your environment. For example, if a user wants to connect to a service like a file share or a database or a web application, they can use Kerberos to authenticate themselves. Kerberos was originally developed at MIT, but we're going to focus on how it's used in a Windows environment. It's defined by RFC 4120, so if you get really curious about the details like me, you can read all about it there. Kerberos uses symmetric key cryptography, so no private keys, public keys here. Instead, everyone has their own secret key. In the little diagram, we can see that the user has their red secret key, the service has their own green secret key, and for our purposes, the secret key is that entity's password hash. Because you're the only one who knows your password, only you should be able to make that hash. And if you have that secret key, then you can prove your identity. There's a central authority in Kerberos called the Key Distribution Center, or KDC, and in a Windows environment, this is the domain controller. The KDC has its own secret key, that dark blue one in our diagram, and the KDC is responsible for enforcing authentication in the environment. The KDC can do this because it also has a copy of everyone else's secret key. We can see that copy of the user's red key and the service's green key in the diagram. A user can prove to the KDC that they control their secret key, and the KDC uses its copy to verify the proof. If the KDC accepts this proof, it will return a ticket to them. We'll talk about these tickets more soon, but this ticket from the KDC can be used as proof to authenticate to other services. I kind of like to think of it like those rides at the county fair. You can buy a ticket from the booth and then hand it to the ride, and the ride knows you've paid without handing them money directly. Basically, same concept here. In Kerberos, the user basically takes the ticket from the KDC and presents it to some service. The user is saying to the service, look, I proved who I am to the KDC accepted that and gave me this ticket. Now this ticket proves who I am to you. Please give me access. So, how does a user prove their identity to the KDC and get that ticket? It all starts with the Authentication Service Exchange. This is the process of how a user authenticates themselves to the KDC. The user first logs into the system with their password. The password is hashed, and that becomes their secret key. So we have that in red in our diagram. They use that secret key to encrypt a timestamp of the current time. The encrypted timestamp is sent to the KDC along with their username. The KDC receives this request, and it takes that incoming username to look up the expected secret key for that user, since it has a copy of everyone's secret key. Once it has the key for the user, it will decrypt the encrypted timestamp and check the result. If it was the right key, it can decrypt the timestamp and prove that it was correct. The KDC will approve and know that the timestamp must have been encrypted by someone who has the secret key. So it has to be the authentic user. Then it starts to generate its response. The KDC will generate a brand new random temporary key. This is called the logon session key, and we have that as purple in this diagram. The KDC finishes up by sending back its reply in a data structure called the ASREP. That's short for Authentication Service Reply. So to summarize, the user has hashed their password and encrypted a timestamp. That was sent to the KDC, who decrypted and checked the timestamp using the KDC's copy of the user's secret key. If it was successful, it will return an ASREP. Let's take a look at what's inside that ASREP data structure. So this is a simplified representation of the ASREP data structure. There's three main parts. First, there's the CNAME, which is just the authenticated user's username in plain text. So if I'm authenticated, the CNAME might look something like Jake K. Then there's the ink part in red. This is encrypted with the user's secret key. Because the user has the secret key, they can decrypt and read the information in the ink part. So this is readable by the user. It has a copy of that purple logon session key and some additional information about the response. The third part is the ticket. Notice that it's in blue. The ticket in the ASREP is encrypted with the KDC's secret key. The user can't read the contents of the ticket. They know the ticket's there, but it's just an opaque encrypted blob of data. The ticket in the ASREP is called the Ticket Granting Ticket, or TGT, because as we'll see in a moment, this is used to obtain more tickets. So the user will extract this ticket from the ASREP and save it for later. Great, so at this point, the KDC has authenticated the user and trusts that they are who they say they are. The user got a ticket granting ticket from the KDC as proof of successful authentication. But what if the user wants to access another service like we mentioned earlier? What if they want to access a file share or a database? Well, there's two additional steps for that. The next part is the ticket granting exchange. Again, this is between the user and the KDC, no interactions with the service quite yet. Here's where the user gets a ticket for a specific service by supplying that ticket granting ticket from the last step. Like before, the user encrypts another timestamp, but now uses that logon session key that the KDC created in the previous exchange. Notice that it's using the purple key in the diagram. The user extracted this out of the ink part of the ASREP, and that was that red user-readable part. Now the user sends the encrypted timestamp, the ticket granting ticket, and the service's name to the KDC, basically saying, hey, I want access to this service. Here's my TGT that you sent me last time, and here's a timestamp encrypted with the logon session key. First, the KDC decrypts the TGT with its own secret key to make sure that it's authentic. Notice that it's decrypting with the dark blue KDC secret key. Once decrypted, the KDC extracts the purple logon session key from the TGT, and with the session key, the KDC decrypts the timestamp to make sure that it's correct. If that all works, then the KDC has accepted the request. All looks good. Time to start building the reply. The KDC generates a new random key. This is called the service session key, and we're going to have it in yellow. The KDC replies to the user with another data structure called the TGS-rep. Well, since this is the Ticket Granting Service Exchange, TGS-rep stands for Ticket Granting Service Reply. So let's take a look at that data structure. Well, hey, this looks pretty familiar. This looks a lot like the last one. We have three parts here too. Again, first part is just the username. The second part is the ink data, and notice that it's purple this time. This section of the TGS rep is encrypted with the logon session key. Well, the user has this key from before, so they can decrypt this section and read its contents. So again, the inc data section is readable by the user and contains that new service session key, the yellow one from before. The last part here is the service ticket. And notice that this is in green. This section is encrypted with the target service's secret key. Of course, the KDC has this because it has a copy of everyone's secret key, but the user does not. The user can't read this section, only the KDC, and the service could read this. The service ticket has another copy of the service session key, that yellow key, some information about the ticket like flags, and it also knows which user the ticket was given to. The service ticket also has the pack. This is at the bottom there. We don't need to worry too much about it, but let's just say that it has some user authorization data, like what groups they belong to, and a whole lot more. There's lots of information about the user in here, and this pack information is signed by the KDC, both with the service's secret key, that green signature, and the KDC's own secret key, the dark blue signature. Because of these dual signatures, you really can't tamper or edit with any of the data in the pack. Cool. So now the user has a service ticket specific to some service. It's finally ready to go actually authenticate to the service itself. We're in the home stretch. Notice in the diagram that the user is talking to the service directly now, not the KDC. The user still has their red secret key and the yellow session key. The service has its secret key in green. The user starts by encrypting a timestamp with the service session key, that yellow one extracted from the TGS rep. It sends this encrypted timestamp to the service along with the service ticket. Basically, the user is saying to the service, here's an encrypted timestamp and here's a service ticket from the KDC. That service ticket proves the KDC trusted me, and it's encrypted with your secret key, so you can prove it yourself. Well, the service will do exactly that. It will decrypt the service ticket with its secret key to check that it's valid, and if it works, it will extract the service session key, the yellow one, that's inside the service ticket. With the yellow session key, it will decrypt the timestamp from the user. It'll make sure that it decrypts properly and isn't too old. As an optional step, the service can check the signature in the pack to make sure that it hasn't been tampered or edited in any way. And if all that passes, the service will trust the user. Effectively, the service is saying, yep, you could only have that information if you authenticated to the KDC, and since you have a valid service ticket from the KDC, I'll trust you are who you say you are. Now they can talk to each other. The user can send more requests, the service trusts the user, and they have authenticated communication. Whew. All right, that was a lot. So let's bring all three pieces together and take a look as a whole. So when authenticating to a service using Kerberos, there are 3 steps. In the first, the authentication service exchange, the user uses their secret key to prove who they are to the KDC. The KDC returns a ticket granting ticket, or TGT, if that's successful. In the second step, that ticket granting service exchange, the user sends that TGT back to the KDC and asks for a service ticket to a particular service. The KDC inspects what the user sent and will return a service ticket. And in the final step, the client-server exchange, the user sends the service ticket to the service itself. This proves that the user performed the first 2 steps. The service can decrypt the service ticket, prove that it's valid, and then the user is authenticated to the service. So that's Kerberos in a nutshell. We can see how these protocols allow us to keep our secret keys secret. There's a lot of trust in the KDC, which acts as the gatekeeper and hands out these tickets for further access. And we can see how these tickets are passed around and used to verify authentication between entities in the environment. So far, we've talked about one user connecting to one service, but in the real world, things get a bit messy. So let's consider a web application, and we'll call this Service 1. Users can authenticate themselves to Service 1 using the protocol that we just talked about, but Service 1 also connects to a database that we'll call Service 2. When service 1 accesses service 2, it wants to use the original user's authorization to do so. That is, when service 1 reads from service 2 should know that it's actually the original user trying to read from the database, and service 2 should enforce that user's authorization. This is sometimes called the double hop scenario. The user is authenticated to the web application, service 1, but also wants their authorization applied to actions against the database, service 2. It's not just limited to web apps and databases. The second service really could be anything, another server, a file share, whatever. But the key issue is, how does service 1 pass the original user's authorization to service 2? That's where delegation comes in. We're delegating authorization from the user through service 1 to reach service 2. There are 3 types of delegation in Windows, and we'll talk about those. On the right side, you can see where they would be configured in the Active Directory UI. The red option is no delegation, blue is unconstrained delegation, and so on. So these different types have evolved over time. They're each a little bit different, and we'll go into each of those. The first is unconstrained delegation. This is old, it should not be used anymore. Basically, the user's TGT gets embedded in the service ticket. When service 1 gets the service ticket, it can pull out the user's TGT. And if it has the user's TGT, it can impersonate that user and get more service tickets to any other service. This is way too much access. It is not recommended anymore. Actually, in an email exchange I had with Microsoft, they said that if you find unconstrained delegation in your environment, you should, and I quote, kill it with fire. I liked that one. Since this was too much access, Microsoft introduced constrained delegation. So in unconstrained delegation, service 1 can delegate authentication, that is, impersonate the user to any other service. But with constrained delegation, service 1 can only delegate authentication to a pre-configured list of services. So we're able to lock down the services where service 1 can pass the user's authorization. There's a couple of types of constrained delegation. We have classic and resource-based. And the key difference between classic constrained delegation and resource-based constrained delegation is the direction of trust. So we'll start with classic on the left. With classic constrained delegation, we give a service a list of services that it is allowed to delegate to. For example, service 1 is allowed to delegate to this database and that file share, and that's it. This list of delegation targets is stored in service 1's allowed to delegate to list in AD. Resource-based constrained delegation goes the other direction. So instead of configuring who service 1 is allowed to delegate to, we can configure which services service 2 will accept delegation from. So for example, with the resource-based constrained delegation, we could say, my service 2 database will only accept delegation from web app A and web app B and nobody else. So we set that in service 2's principals allowed to delegate to account list in Active Directory. So we're either saying service 1 is allowed to delegate to and setting that in allowed to delegate to property for service 1, or we're going the other direction and we're saying service 2 will accept delegation from and then setting the principals allowed to delegate to account property on service 2 in Active Directory. Let's see how this delegation thing actually works. How can service 1 actually talk to service 2 on behalf of some other user? So we start with service 1 authenticating itself to the KDC and obtaining a ticket granting ticket. This is just like the initial authentication service exchange we saw before. Nothing new here, just service 1 authenticating itself to the KDC. And in the second box, service 1 uses that TGT that it got to request a service ticket to itself for a target user. So if the TGT is accepted, the KDC returns a service ticket for service 1 authenticated for the target user. Service 1 at this point has a ticket for some user to service 1. Now, this would allow Service 1 to perform actions against itself as the target user, but that's not really useful. In the third box, Service 1 sends that service ticket back to the KDC to obtain a service ticket to Service 2 on behalf of that same user. Essentially, Service 1 is telling the KDC, hey, the target user authenticated to me, and here's their service ticket to prove it. I would like to exchange this for a service ticket to Service 2 on behalf of that user. Well, the KDC will confirm and returns a service ticket that is valid for Service 2, authenticated as the target user. Now, Service 1 can present that service ticket to Service 2, prove they are authenticated as the target user, and effectively impersonate that user to Service 2. As far as Service 2 is concerned, or even aware, they're directly talking with the user, not Service 1. So clearly this is pretty powerful functionality. Service 1 can take a series of steps to obtain a service ticket to Service 2 and impersonate an arbitrary user. Hopefully this is setting off some alarm bells for you. This is an authentication scheme that includes impersonation. Well, because of that, there are some protections in place. First is that you can protect certain user accounts from being impersonated through these extensions. To do that, you have two options. You can configure user accounts as sensitive and cannot be delegated. That is applied to the account itself, and you can see a screenshot of that configuration in Active Directory on the right there. Or you can add them to the protected users group. So any members of the protected users group should never be delegated, and these are probably privileged users. Secondly, services are not allowed to perform this delegation by default. So instead, an admin must explicitly configure which services are allowed to delegate authentication to which other services. And that could be either classic or resource-based constrained delegation. Going back to our overview for a moment, let's zoom in on this second section. Remember, this is where Service 1 uses its TGT to get a service ticket to itself on behalf of some user. This is called the S4U2 self exchange. And note that this is an extension built on top of Kerberos by Microsoft. So not default Kerberos behavior, but an extension provided by Microsoft to support these constrained delegation scenarios. Well, it's pretty similar to obtaining a service ticket through the normal ticket granting service exchange, but there's one key difference. After validating Service 1's TGT, the KDC has to check if the specified target user is protected from delegation. Remember, an account can be configured as sensitive, or it could be a member of the protected users group. If either of these are true for the requested user, then the service ticket that's returned will not be forwardable. That is, in its metadata, the forwardable bit will be set to 0. The KDC will still return the service ticket to Service 1, but this forwardable bit signifies if the user is allowed to be delegated or not. Okay, so going back to our overview, we've completed part 2. We have a service ticket to Service 1 on behalf of some user, and that ticket may or may not be forwardable. Depends if the user is actually protected or not. Well, we want to turn that into a service ticket for Service 2. So we continue on to the third section. This is the S4U2 proxy exchange. Again, this is a Microsoft extension, not originally defined Kerberos functionality. Here, Service 1 sends that service ticket back to the KDC asking for a service ticket to Service 2. And the KDC has to perform some checks to enforce those protections that we mentioned earlier. So first, the KDC checks if Service 1 is allowed to delegate to Service 2, or if Service 2 accepts delegation from Service 1. Basically just checking that either classic or resource-based constrained delegation has been configured, at least in one of those directions. If not, it exits with an error, no service ticket is returned. Well, if it does succeed, then it continues on and performs a second check. The KDC checks if the service ticket is forwardable or not, If the ticket is not forwardable, that means that the requested user is supposed to be protected from delegation. So if the service ticket is not forwardable, that is, the forwardable bit is set to 0, then the exchange would fail with an error. But if the service ticket is forwardable, meaning the forwardable bit is set to 1, then both checks have passed and a new service ticket to service 2 is returned. So when the process works as intended, here's how it looks overall. Service 1 authenticates itself to the KDC to get that TGT. Then Service 1 uses the S4U2 self process to get a ticket as the target user to itself, Service 1. Then it uses the S4U2 proxy request to get a ticket to Service 2 as that user. With the final service ticket in hand, Service 1 can make requests to Service 2 as the target user. Now let's focus in on one part here. Recall that it's providing the service ticket received from the S4U2 self request as evidence. So this service ticket comes back from the S4U2 self request is pretty important. Well, let's take a closer look at the structure of that ticket. Well, we know what these responses look like from before. And remember, if the user is protected, the forwardable bit will be set to 0. And this is going to be checked in the upcoming S4U2 proxy exchange. But there's a problem here. Let's think about this for just a second. Recall that the service ticket is encrypted with Service 1's own secret key. Well, Service 1 has that key. It can decrypt the ticket and just make it forwardable. So even if the ticket comes back in the S4U2 self-exchange is not forwardable, Service 1 can make it forwardable. So how does our overview change with this information? Well, the first part proceeds like before. Nothing's different. Service 1 still has to authenticate itself to the KDC and get that TGT. But now when it uses the S4U2 self request, even if the service ticket that comes back is not forwardable, for example, if the target user is protected from delegation, then Service 1 can make it forwardable by decrypting the ticket with its own secret key, flipping the forwardable bit to 1, and just re-encrypting the ticket. Now, since the service ticket is forwardable, when the KDC checks during the S4U2 proxy request, all those checks we talked about are going to pass. It appears as if Service 1 is allowed to delegate as that target user, so Service 1 gets a ticket to Service 2. So by decrypting the ticket, flipping that single forwardable bit from 0 to 1, we can impersonate protected users. Well, if you've hung in there with me so far, you must be ready for a demo. You might be thinking, okay, I've heard enough of this guy talking. Please, no more diagrams. I just want to see what this actually looks like. So I hear you. Let's jump into our demo. So for this demonstration, we'll be working with a small Windows domain that I set up. There are 3 total computers with 2 users that we'll be focused on. So for the computers, there is the required domain controller, and there are 2 servers named Service 1 and Service 2. User 1 is a local admin on Service 1 and has no access to Service 2. Similarly, User 2 is a local admin on Service 2 and has no access to Service 1. We're going to play the role of an attacker, and as an attacker, we've compromised the User 1 account. So we have command execution on Service 1. Our goal is to pivot to the Service 2 server, specifically by impersonating User 2 and using their authority. So we'll check out a couple of different scenarios, and we'll see how the Bronze Bit Attack, the vulnerability we've just discussed, can be leveraged to accomplish this goal. Okay, so we're in our demo environment now, and we're on the domain controller. We're going to be using the Active Directory UI to take a look at its initial configuration, see what the environment looks like, make sure that it's as we described a second ago. So Our first thing we're going to do is open up the computers directory, and we're going to see that we have two servers here. We have service 1 and service 2. If we take a look at the configuration for service 1 and go to its delegation tab, we can see that it's allowed to perform delegation to service 2. This is classic constrained delegation. We can see that it's explicitly configured that service 1 is allowed to delegate to the various services on the service 2 server. Great. So let's take a look at our users in this environment as well. We have two users, user 1, who's an admin on service 1, and we also have user 2, who's an admin on service 2. Let's go take a look at the account configuration for user 2. And under here, we'll see that it is marked as account is sensitive and cannot be delegated. So like we mentioned earlier, this is an explicit protection to protect against being impersonated through the delegation process. So user 2 has that protection in place, and just for good measure, let's take a look at its group memberships as well. And as we can see, user 2 is also a member of the protected users group. So really, the user only needs one of these protections to be protected against delegation, but just for good measure, to show the exploit, we're going to have it have both protections in place. So user 2 is also a member of protected users. Great, so we're going to jump over to our service 1 computer. Let's take a look at that. Okay, so we're on service 1 now, and keep in mind in our example, we're considering that we've already compromised user 1, who is an admin on service 1. So we already have command execution on service 1. But let's double check and confirm who we're running as. So currently we are running as user 1, and user 1 does not have any privileges to access service 2. But let's do a quick check. So first, we're going to try to list some contents off the file system of service 2, and we get access denied. Well, that is expected. User 1 does not have any access to service 2. Just to check, we'll also try to execute a shell and open up some command execution on service 2. Let's see. Well, that also fails, but again, to be expected, user 1 in its current configuration does not have access to service 2. So we'll just clear this up and we'll get ready to perform some more interesting commands. So as we're looking into this, I strongly recommend not worrying too much about the syntax of the command itself. If you're interested in that, I would recommend checking out the corresponding exploit blog post that is already on the NetSPI site. So I'll be explaining what these commands do, and I would encourage you to not focus too much on the syntax, rather just trying to understand the operations that we're performing here. So first up, we'll be using secrets dump from the Unpacket framework, and our goal here is to obtain the secret key for service 1. Well, we are already an admin, user 1. We've compromised those credentials here. So since we're an admin on service 1, we can simply extract the secret key from service 1. And we'll use secret dump to do that. So we're passing in the password for user 1, and we're running that against service 1. There's a lot of information in this output, but we're only interested in a few key pieces. So first, we have this AES256 hash, and remember, the secret key is just a password hash. So this is one representation of that secret key. And we're also interested in this NTLM hash of the secret key. So these are just two different representations of the same machine account password. So we want these secret keys so that we can perform the upcoming steps and start interacting with the KDC and requesting tickets. So we've used our privileged access on service 1. We've extracted out the secret key for service 1. And now we're going to start interacting with the KDC, performing the S4U2 self and S4U2 proxy exchanges we were just discussing. So this command, also from the Unpacket framework, is going to try to get a service ticket to service 2 as user 2. So let's take a look at these parameters. So first, we're passing in that we would like to get a ticket to the CVE service for the service 2 server. Specifically, we would like to impersonate user 2, who is an admin on that box. we can see that we're passing in those hashes that we just extracted out. These are our secret keys that we need to request these tickets at all. And we're specifying that this is coming from service 1, who we know is allowed to perform delegation to service 2. So let's go ahead and run our command. And we get an error. Well, the error is not too unexpected because user 2 is protected against delegation. We can even see in the output either service 1 is not allowed to delegate, which we know it is, or the ticket is not forwardable. So that ticket not being forwardable is the expected behavior since user 2 is protected. Well, we've just been talking about how we can exactly work around that. So we're going to rerun our command with a slight modification. So this looks very similar to before, but we can see at the very end, we've added this additional flag here. So looking right here, we have the force forwardable flag, and this is the exploit for the Kerberos Bronze Bit Attack. So this is something that I added and contributed to the packet framework to execute the steps that we've been talking about so far. So let's go ahead and run it and we'll talk through what's happening behind the scenes. We get a little bit different output this time, and as the output suggests, we're running through a couple of steps. First, we perform that S4U2 self step where we're getting a ticket for user 2. It comes back and is initially not forwardable because the user is protected. We have the service ticket, so we have the service secret key, the hashes right there. So we're able to decrypt the ticket, flip the bit, make it forwardable, and then send that forward in the S4U2 proxy exchange. The result of that is a service ticket to service 2 authorized as user 2. Well, great, we can see that we've saved that in our user 2 cache after forcing the forwardable bit on the service ticket. So let's clear this out, get a clean slate. But right now we have the ticket saved in a cache file on disk. We'd like to load that into our Kerberos cache in memory. So we'll use Mimikatz to load that. There are lots of ways to load a ticket into memory. This one just happened to be easy and has nice output because the output confirms that we injected it okay. We are injecting this for service 2 as user 2. Cool. Let's go ahead and use our access. So before we saw that this same command of trying to read the file system on service 2 failed, but now it executes successfully. Let's try to open up our shell. And that's looking pretty good. What we're going to run first is the whoami command to see who we're running as on service 2. And we're running as user 2. We're also going to do a quick double check of the host name, service 2. So we can confirm that we're running as user 2 on service 2, and we're impersonating them using the Bronze Bit exploit, which works around the protections that they already had because they are marked as sensitive and cannot be delegated, and they are a member of the protected users group. Oh, great. We've successfully pivoted from having access on service 1 to having access on service 2. What we'll do here on service 1 is we're going to do a quick reboot of the computer just to clear out the cache, make sure we're not holding on to any authenticated sessions or things like that, and we'll set up scenario 2. Alrighty, we're back on the domain controller and we're checking out our environment configuration that has changed for scenario 2. So we're going to take a look at our 2 servers. We still have service 1 and service 2, but the configuration has changed here. So specifically, service 1 is no longer allowed to perform delegation to service 2. That classic constrained delegation relationship that used to be there is gone. So no more delegation between 1 and 2. And just as a quick check, we see that service 2 doesn't have that either. But the security settings for service 2 have changed. Specifically, user 1, who we've compromised, now has read and write permissions over the service 2 Active Directory computer object. So just to be clear, user 1 isn't an admin on service 2, anything like that. Rather, this is an Active Directory permissions change where user 1 can change the service 2 AD computer object. We'll see how we'll use that shortly. Alrighty, we still have our two users just like before. User 1 is an admin for service 1, no direct access to service 2. User 2, just like before, still an admin for service 2. It's still labeled as sensitive and cannot be delegated, and it's still a member of the protected users group. So let's hop to service 1 and take our attack from there. Alrighty, so we're on service 1 now, and just to confirm, we're executing commands as user 1. We have a clean reset, so we no longer have access to service 2. We can't read from the file system. We can't open up a shell. Brand new slate. We've confirmed user 1 doesn't have access to service 2. Cool. That's as expected. So this is where our attack scenario starts to differ from the previous one. The first thing we're going to do is import PowerMad. So PowerMad is a functionality published by Kevin Robertson, and we'll see how we'll use that in just a moment. So the function we'll call from there is new machine account. This will add a new computer object within Active Directory. So specifically, we're going to name ours attacker service, and we're going to provide a password for this computer object, in this case attacker service password, and we'll see how this can be created in Active Directory. By default, any user, any domain user within the environment is allowed to create these machine accounts. So let's take a quick peek back on the domain controller. So over here on the domain controller, if we go to our computers directory, we're going to refresh that here. And we can see that we have a new computer object, our attacker service. So there's no real server actually associated with this, but we don't need that. We now have an extra entity in the domain that we have the name of attacker service and control of the password for, since we set the password ourselves. Great. We'll continue on. So we're back on service 1. We have our attacker service, and what we're going to do is use Mimikatz. Lots of different options here, but we're choosing Mimikatz to compute the hash for that password. So remember, the secret key for an entity in Kerberos is the password hash. So we can compute that. We have the password. We set it ourselves. We know it is for the attacker service user, and we have the domain. So we're going to go ahead and compute those hashes. And like we mentioned before, there's two that we're interested in. There's the AES-256 version of the hash, and there's the NTLM version of the hash. These are the secret keys for the attacker service computer object. Okay, well, we also mentioned that we have, as user 1, new permissions over the service 2 computer object. This is part of this particular scenario. We're assuming we have some read-write permissions over that object. Let's see how we can actually use that here. So we're going to import some Active Directory PowerShell functionality, and then we're going to perform an update. Specifically, against Service 2, we're going to update its principals allowed to delegate to account list to include our attacker service. So this change that we just made essentially set up resource-based constrained delegation. Service 2 will now accept delegation from attacker service. And notice that we didn't have to be an admin on service 2. Just by having write permissions over the AD computer object, we're able to set that property. And we can use our read permissions to confirm that it was set correctly. And we've updated that computer object within AD to set up this resource-based constrained delegation. So we'll clear that out, and the rest of the attack is actually pretty much the same. So we're going to use the same getST program from the Impacket framework. Again, we're going to specify that we want a ticket for service 2 as user 2, but our hashes are the hashes we calculated for the attacker service. So we're using our new attacker service, its secret keys, and we're including the force forwardable flag. We have to do this because user 2 is protected against this. So we're including our exploit to get past that extra step of protection. So we get the ticket from S4U2 self, we force it to be forwardable with our exploit, and we have written to disk user2.cache. We're going to load that into our Kerberos cache in memory. So we now have a ticket to service 2 as user2 injected into our Kerberos cache. Let's go ahead and use that permission. We now can read the contents of the file system on service 2, just as you'd expect. Just like before, we can open up a shell and get command access on service 2. We can see we're now executing as the admin user over there, user 2, confirming we're on service 2. And with this level of access, we can make some changes to the local computer. Specifically, let's list out the admins over there on service 2. We already know it's user 2, no surprises. But what if we'd like to add our previously compromised account? Specifically, we can add our previously compromised user 1 account as a local admin on user 2. So we make that change, we read that change right back out and confirm it, and now user 1 is also an admin on service 2. With our local admin access, we can go ahead and connect via RDP as user 1. So we're just demonstrating that here. We can make that connection and we drop in our previously compromised creds for user 1. And there we go. So by just having the existing write access over the service to computer object, we could use the out-of-the-box default permissions of domain users to create machine accounts. With the permissions over service 2, we set up a resource-based constrained delegation relationship, and then we bypassed the permissions for the protections for user 2 from delegation with the Kerberos Bronze Bit exploit. That allowed us to pivot in our environment, moving from service 1 to service 2 with administrative access. Welcome back from the demo. I hope you enjoyed. Now that we understand Kerberos itself, we know the Bronze Bit vulnerability, and we've seen it in action, I'd like to briefly touch on Microsoft's fix for this issue. In November and December of 2020, Microsoft released a series of updates to enable ticket signatures. These updates add a signature of the ticket's contents into that pack data structure. Because the pack is signed by the KDC using both the service's secret key and the KDC's own secret key, it's effectively tamper-proof. So if you tried that same Bronze Bit attack again, where you're flipping the forwardable bit, the KDC will detect that change when it looks in the pack and validates that ticket signature. So this change will get detected during the S4U2 proxy exchange. It'll reject the request, and the service can't obtain the ticket to impersonate the protected user. And as of February 9th, this is now the default enforced behavior. Before we close, I'd like to give a special thanks to all of the following individuals. As security researchers, we're all standing on the shoulders of giants, and I'm truly grateful for the excellent research these folks have published and how they've helped me with this vulnerability and its exploit. So a heartfelt thank you to all of them. And thank you as well. So I really appreciate you joining me on this journey. I really hope you enjoyed, and I'll be available for questions.